Hi, everyone. Welcome back to MATA02, the magic of numbers. I would like to thank all of you who are here in person, as well as all of you who are joining in from online. So now, as you know, today is the first of the 2-week transition period in which I will be doing the simultaneous live stream online, as well as, giving my lecture to you guys in person. I sort of wish I had planned a more interesting and exciting lecture for our first day back, but don't worry, there will be lectures in which the fact that you're here in person actually makes a difference. Hopefully in the next couple of weeks, I'll have a couple lectures planned where there's actually some use for you being here as opposed to just online. While we're doing this, the participation is still via the chat, which you can see up there. So I'll still be asking you to vote on things, whether you're here in person or online. Just to give another announcement, I brought some candy for you guys on the first day. Please feel free to take one on your way out. Obviously, unfortunately, for those of you who are just online, you don't get candy, but that's how it goes. So, any questions before we get started? And first, a party welcome to everyone, especially those of how many of you guys, is this your first in-person class? Ever? Or just this, wait, ever? Wow, okay. Well, welcome. I hope I don't disappoint. I probably will. It's a math class, but hopefully you guys will have lots of fun in-person classes. But let's go ahead and get started. And we are going to start with a topic that you guys have already seen a little bit of. Oh, sorry. Okay, yeah. So a topic that you guys have already seen a little bit of, which is least common multiples and greatest common divisors. And we're going to redo this via factorization. I know some of you already were using this method instead of the Euclidean method on the first homework, and we're actually going to formalize it. So how does it actually work? What can you do? Why is it sometimes easier than doing it the other way? So let's remind ourselves, what are greatest common divisors again? Well, suppose b divides n. Well, then we happen to know that the prime factorization of b must have exponents less than or equal to the prime factorization of n, right? Because if it doesn't, then it can't divide it by what we showed last time. So that means that if d divides both n and m, then all of those exponents must be less than or equal to both those in both n and m. So for example, if we have, and so this means that the greatest common divisor lets us exponents exactly equal to the smaller of the exponents in both of them. So what exactly does that mean? Well, let's see. Come on, give me a pen. There. So for example, if we have 24 is equal to 2 cubed times 3, and we have 54 is equal to 2 times 3 cubed, I think that's right, 27 times 2, yep. So then the greatest common divisor of 24 and 56 will then be equal to 2 to the 1 times 3 to the 1, which is equal to 6. So that's by using this particular way of computing the greatest common divisor. And of course, we have the other way, which we all learned and you guys did on the first quiz, of using the Euclidean algorithm. So if you did it that way, instead, you would have gotten 54 is equal to 24 times 2 plus 6. 24 is equal to 6 times 4, and therefore the greatest common divisor of 24 and, oh, sorry, that shouldn't be a 56, that should be a 54. And that's 54 is equal to 6. For the record, if I make mistakes like this in person, you can just feel free to shout at me. Feel free to interrupt me when I make mistakes like that, or you can put it on chat and I'll see it eventually. But if you're in person, you can't actually just shout at me when I do something really silly. Okay, so that's greatest common divisors. We have 2 different ways of doing it now. And notice that this way is really, really easy if you know the prime factorization. If you know the prime factorization of 2 numbers, then you can basically read off the greatest common divisor. Well, what about least common multiples? Well, we already know that there's a close relationship between greatest common divisors and least common multiples. And of course, you could compute the least common multiple by multiplying your 2 numbers together and then dividing by the greatest common divisor. But if you have the prime factorizations, it's actually even easier than that. What do I mean by that? Well, let's remind ourselves what the least common multiples were. Well, the least common multiples, suppose m is a multiple of a, and that means that the prime factorization of m must have exponents greater than or equal to the prime factorization of a. So m must have exponents greater than or equal to. And so if it's a multiple of 2 different things, so if it's a common multiple, then all of those exponents must be greater than or equal to those in both a and b. So this is sort of the converse of the greatest common divisor, right? So the other one was the smaller of the exponents. This one's the bigger of the exponents. And so this is pretty straightforward. So when we do this, let me do this in red again. So we again have 24 is equal to 2 cubed times 3. And 54 is equal to 2 times 3 cubed. Well, when you're actually, the least common multiple of 24 and 54 is unequal to 2 cubed times 3 cubed, which is equal to 8 times 27, which should be equal to 216 if I wrote down my numbers correctly. And of course, we can directly check that. You can do it either using the greatest common divisor method, or you can just check your check your multiples, of course. So let's start by checking our multiples. So if you have 24, 48, 72, 96, 120, 144, 168, 192, and 216, those are the multiples of 24. And well, what are the multiples of 54? Just 54, 108, 162, and 216. So that is correct. And so we now have two different ways of finding least common multiples. We have the way that uses the factorization, as well as our old method. And as many of you may have found during when you were solving these things, often it seems a lot easier if you know the factorization, right? You just have to read off the exponents, and you don't have to go through the entire process of either labeling all these things or using the Euclidean algorithm. So you might wonder, well, why don't we always just use the factorization? Does anyone want to answer that, either in chat or in person? Yeah, go for it. Yeah, so the difficulty is like this is all contingent on, that's exactly right. What was your name again? Thank you. Yeah, sorry, I'm going to try to learn names. I'll probably butcher them all because, well, that's what professors do. But anyway, so that's completely right. It's because factorization is itself hard. And so we can't actually factor most big numbers. But if you happen to know the factorization, then it is actually easy, because then you just read off the exponents. Well, let's keep on going. So, well, a while ago, I stated that the least common divisor times the greatest, the least common multiple times the greatest common divisor is just the product of the two original numbers, right? But I didn't actually prove that in class. So why is that true? So like, it's a little bit hard to see when you're just defining them as least common multiple and greatest common divisor. Like for greatest common divisor, we have this weird way of using this Euclidean algorithm. For least common multiple, well, the naive way is just to list them all out. And somehow those don't seem obviously connected. But of course, when you look at, this using the factorization method, it is obvious that they're connected. And so this is actually one of the ways you can show that, which is that, well, if you happen to know what the prime factorizations are, so let's say A is equal to, let's write this out as 2 to the C2, 3 to the C3, 5 to the C5, 7 to the C7, 11 to the C11, and so on. So some prime factorization. So each of these C's are the exponents for those values. And let's say we have B. Actually, let me write this in a different color just to make it obvious. Oh, come on. And we have B is equal to 2 to the D2, 3 to the D3, 5 to the D5, 7 to the D7, 11 to the D11, and so on. So when you multiply these two together, what you get is you add them together, right? So this is equal to, where am I? Let's put this in blue. So AB is then equal to both of these multiplied together. So you end up with 2 to the, let me do this all in blue. Oh, come on. Sorry, it's a little bit harder to do this interface. That's 2 to the C2 plus D2, 3 to the C3 plus D3, 5 to the C5 plus D5, and so on, right? I'm not going to write them all out. And so clearly, when you're multiplying these numbers, if you know the prime factorization, this is one way of knowing what the product of the two is. You just add together the exponents. But there's another fun fact, which is that, and this is generally true. So note that it's always true that x plus y is equal to the smaller of the two numbers, so the minimum of x and y, plus the bigger of the two numbers, the maximum of x and y, right? And this sort of makes sense intuitively, right? So if you take two numbers and then you say, well, I'm going to take whichever one's smaller and take whichever one's bigger and adding them together, that's the same as just adding the two together. Now, this doesn't seem that important, but it turns out that this is what allows us to prove that this thing is actually equal to, so that's equal to 2 to the minimum of C2 and D2 times 3 to the minimum of C2, D2, and so on, times, oh, sorry, let's MIN, 2 to the maximum of C2, D2, 3 to the maximum of C2, D2, and so on. But of course, the left there, when you take the minimums, that's just the greatest common divisor of A and B. And the right there is just the least common multiple of A and B. So this is actually one of the ways that you can prove that the greatest common divisor and least common multiple, when multiplied together, give you the product of the two. So let's have you guys try this out. So any questions before we go ahead? So basically what we're doing is we're now going back and proving some of the results that we were already using for computations. So let's try it out. What is the greatest common divisor of 3072 and 896? So let's do this step by step. So step one, what is the prime factorization of 3072? Excuse me, sorry, talking too much. When I'm doing this all online, I can mute myself whenever I cough, but that's less possible here in person. Okay, so it looks like we have, oh, okay, people are replying. We have a lot of D's. So 3072. People think that this is 2 to the 5th times 3 to the 5th. So let's check to see if this is right. Well, let's try to start out factoring this. So one of the things that you have to be really careful is a bit of an issue for having the slide. Chat is it seems like sometimes people just like jump onto whoever puts down the first answer. So whenever you have to be a little bit careful about that. So what is 3072? 3072, well, you might notice that this is divisible by 3, right? So, I mean, you have noticed it's divisible by 2, but you can also notice it's divisible by 3 because if you add together the digits, 3 plus 7 plus 2, that is 12, which is divisible by 3. And so this is equal to 1024 times 3. And I happen to know that 1024 is equal to 2 to the 10th power. You can also see this by just dividing by 2 over and over again, since it is even. So this is 2 to the 10 divided by 3. So the actual answer here is C, not B. So you have to be a little bit careful when you're doing these factorizations. That you do need to get them right. And if you get the factorization wrong, then your greatest common divisor and least common multiple will, of course, also be, well, quite wrong. Okay, well, let me zero that out and let's try again. So what's the prime factorization of 896? Oh, wait, sorry, not that one. So what's the prime factorization of 896? It's one of the answers that's on the top as well. So let me give you a hint, which is that you might try dividing by 7. Okay, so yeah, it looks like many people got this. So 896 is equal to 7 times 128, which is equal, I happen to know 128 is 2 to the 7 times, is just 2 to the 7. So of course, you don't need to have memorized all your powers of 2. I happen to because they turn out to be super helpful. But even if you don't have the powers of 2 memorized, you can, of course, just divide by 2 over and over again, and that will give you, this is 2 to the 7th times 7. And so this here is actually, let me put this in a different color, is actually there. Okay, and lastly, well, how do we finish solving this? Well, you get the smallest of each exponent. So how do we do that? So what is the greatest common divisor of these two? GCD of 896 and 3072. Well, you have several different things here. So you have a 2, you have a 3, and you have a 7. So what is actually the greatest common divisor? Okay, so we have B. Yes, because this 7 is the minimum of 7 and 10. And this 3, well, there's only a 3 in one of them, so it's 3 to the 0. There's only a 7 in one of them, so that's also sum to the 0. So these all cancel out, and that's just 128. Okay, and this is just one other way of solving for these greatest common divisors and least common multiples. And this way is quite useful in some respects whenever you have a factorization. But more importantly than that, it allowed us to prove the fact that we were using that the greatest common divisor times the least common multiple is the product of the two numbers themselves. So any questions before we move on? Okay, so that is sort of finishing up some of the material from last lecture that we didn't get to. And I'm going to try really hard to talk about relative primes today because you guys need that for your tutorials and for your quiz next week. So I'm going to try to do some of that. So let's see, this is lecture 5B.